All right, so the first thing we're going to go through is the exponentials. This one is the one I gave you last time.
Yeah.
So hopefully you brought that with you.
Yes.
And we're going to finish, I don't think that'll take a long time, and then we're going to start on this guy, related rates. But first, definition. There's someone who always says, "Oh my God," like that's not a rule. Power rule. Product rule. Quotient rule.
Times G minus F times G prime over G squared.
Chain rule.
Derivative.
Be careful how you write this. This is not a multiplication. Remember, it's a composite function. The G is plugged into F prime. So I saw some people write on the quiz like they wrote F prime times G prime. That's actually incorrect. Right? It's not a multiplication. Right? This is plugged into the composite function. Derivative of A to the E. Derivative of ln u. Derivative of e to the u.
That's it. By the way, I cleaned the board.
What?
I cleaned it. I erased it.
You did this?
Yeah.
Is that true?
So I better get like flashlight.
Okay, so let's actually move on. By the way, I still have some people getting these things wrong in the quizzes. So we're going to keep doing it until you guys stop getting it wrong. Anyway, so yeah, today we are going to do I think this is 3.6. The important application of derivatives, exponential growth and decay. Again, this is something you're going to see in Math 209, and it comes in actually many subjects, actually.
Can I ask you a quick question? On a test, do you come up with your own questions or do you like look up?
Sometimes I don't mind. Usually I don't.
Because like the ones in the textbook or the ones that I find online are somewhat easier than the ones on the test.
Yeah, it's always the case.
No, that's not true.
Yeah,
No, that's definitely not true. It's the same level of difficulty. It's exactly the same. Okay, so basically there are a couple formulas that you need to remember. And so there's one set for growth. Now there's something called a differential equation. You're going to learn how to solve these in Math 209 and maybe in some other course that you might need it. So for an exponential growth, it looks like this. This is called the differential equation. So if you're asked for the differential equation, it wants you to set up that guy. Then there's the actual, it's the solution to the differential equation. And that guy looks like P is equal to P naught e to the RT. I call it PERT formula because you know, PERT like a shampoo. You guys know that shampoo? Oh, yeah, that was on. Okay. So, for now, that's the differential equation. If you solve this differential equation, which you learn how to do in Math 209, this would be the answer to the differential equation, and this actually tracks P. Right, so here, P is a quantity.
Wait, is it P times E to the R?
P naught e to the RT. There's a P
No.
substitute.
What are those?
Well, I'm going to tell you now.
Okay.
Okay, so P is a quantity that grows exponentially. I.e., changes by a percentage amount. So if you have something that grows by 5% of its current amount, you say it exhibits exponential growth. So that's what the P is. Technically, it's a function of time, so you can think of P as P of t, but a lot of times I'll just write P because I'm lazy. So that's what the P is going to represent. Any quantity that you know grows exponentially, you can call P, and these two formulas will apply. R in this formula and that formula is called the growth constant. And it's basically the percentage growth written as a decimal. Right, so for example, if P grows by 5% per unit time, then that means your R you take as 0.05. You write 5% as a decimal. So that's what the R value is. So that's the guy that's telling you how fast this thing is growing as a percentage of itself. Then there's, of course, T, which refers to time. Units will usually be given. So they'll tell you if it's seconds or years or months. But T will represent time. P naught, P sub 0, is what represents the initial amount of P. It's the amount that you start with. So basically, remember, we can look at the derivative as a rate of change or a rate of growth. And this is basically saying there's something that grows as a percentage amount of itself per unit time. So once we have something like that, we can actually solve it, solve the differential equation. You don't need to know how to do that in this class, but you do need to know what that equation is. When you solve it, you get this guy. P naught represents the initial amount, E is the number E, R is the growth rate as a percentage decimal, T is time. Some other nice things to know, which is really important. It turns out the doubling time is ln2 over r. Doubling time refers to the time for P to double. By the way, that's always what it will be. So that's a formula you can memorize for exponential growth. It will always be ln2 over r would be the time to double. I think here I can show you why that is, because it's this kind of manipulation we'll have to be able to do. Why? So if P doubles, then after the doubling time, we start with P naught, we would have 2 P naught, right? Now your P is the current amount, right? So if I know that P is equal to P naught e to the RT, and after the doubling time, I know that this guy becomes double of what it was before. Then in this case, I can cancel the P naught. To be able to solve for T, I would ln both sides. Here, ln would cancel E. And like ln2 is equal to R times T. In other words, T is equal to ln2 over R. So the time to double will always be ln2 over R. I might call this TD for emphasis, to say it's the time to double. And that is a formula that will always work with exponential growth. And by the way, there's nothing special about doubling. The time to triple would be ln3 over R. Time to quadruple is ln4 over R, and so on and so forth. So something that grows exponentially will follow those equations, and the time for it to double, which is something that they often ask for, how long will it take to double? You can use that guy. Decay is very similar. For decay, your growth rate is negative because you're decreasing. Decay means decreasing. Right? Like you'll say a radioactive substance decays. Right? So in this decreasing, so your growth rate is actually negative, but it's still growing by a percentage amount of itself. So this is the differential equation for something that's decaying. And its solution is P equals P naught e to the minus RT, where P is the current amount, P naught is the initial amount, R is again the rate of the growth rate as a decimal percentage, T is time. By the way, all of this is actually in the handout anyway. One important thing that you'll hear all the time, especially in a lot of your science classes, they'll talk about the half-life. This is the time. Half-life refers to a time. It's the time taken to decay to half the original amount. So you start with 1 gram of a substance to figure out how long it takes to get to a half a gram of the substance. That time that elapses is called the half-life. It turns out the half-life for a substance that's decaying is again ln2 over R. The formula works out nicely that way. It's the same one as the doubling time because we have this negative R over here. So you might ask why. Well, if I want to figure out the time it takes to get to half of what I started with, again, that's the equation I need to solve. I can cancel P naught. I can ln both sides. And so my T would be minus ln of 1/2 over R. Now I told you that the half-life is ln2 over R. Is that different? How do I reconcile that? How is this the same as that? Why is minus ln of a half over r the same as ln of 2 over r? It becomes what?
Because it's on the other side of the.
Negative ln over 2 over r. Because what? How would you apply that?
You can take negative, and that's actually a negative 1. Move it to the 1/2, and then that flips the 1/2 to
Right, so 1/2 is just 2 to the minus 1 power. Which means this negative 1 I can bring down, turns that negative sign to a positive, and I get ln 2 over r. So they're the same. Just apply a log rule. I could also look at ln of 1 over 2 as ln of 1 minus ln 2. The negative signs distribute, ln of 1 is 0, so I just get positive ln 2 over r. You can do it several ways, but it's basically applying a log rule. But it's nice to memorize it that way because it coincides with the growth formula. And so in this case, you might see me refer to the half-life as T sub h. H, H. And that will always be what it is. Half-life is a very important measurement, and so a lot of times the problem will tell you the half-life, and you can just use this equation to figure out the R.
So the problem will tell you that ln 2 over r, the value of that.
Well, let's see what the problem will tell you. Now we jump to the examples. Tons of examples in this, we're going to go through them. Right? So here I gave you the formulas for growth and decay, and what all the pieces mean, and here I show you that it also applies to something called compound interest. So you can think of this as compound interest in a situation where it says compounded continuously. And we have 2 pages full of examples, and the problems won't be very different from this one. Right? In fact, some of these I took straight from finance. Okay. Let's go to examples. So what you're going to need to remember for these guys are, of course, your log rules, your rules for E's and LNs, and you're not going to need much calculus after this. Pretty much just applying the log rules. Okay. So let's start with the first problem. This is from spring 2009. I believe this was problem 4 on diagram. Okay, so let's read it. Let P of T be the population of a colony of bacteria. At 11 a.m. there are 60. At 3 p.m. there are 350. Assume exponential growth. And then there are 3 parts. Find P of T and simplify. What is the size of the population at 4 p.m.? When will the population reach 2,000? Right? So here you have bacteria. Bacteria grows. So I know it's exponential growth. And they even told me there assume exponential growth, but I assume it's growing anyway because bacteria tends to grow. Unless you're trying to kill it. Okay? So how do we start? How do we find P of T? Right, so we know that P of T is equal to P naught e to the RT. Now when you want to find the formula for a specific thing, the 2 things that you need to find is this guy, the P naught. And you will need to find the R. T is the input variable, P is the output variable, so you don't need to find those unless you're asked about a specific point. But whenever they say find P of T, they want you to give them the equation and tell them what this number is and what the R is. So what do we have here? Do I know either of these values here?
Yeah, we can
Which is what?
60.
Right, so it says they gave us a starting point. 11 a.m. is the starting point. Right, so 11 a.m. First of all, I'm going to assume that it's t equals 0. That's where I'm going to start the clock. And I know the initial amount at that point, is 60. So in the beginning of this experiment, or this thing that I'm watching, it starts at 60, time equals 0 is considered 11 a.m. Okay. Now it says at 3 p.m. there are 350. How do I use that fact? How do I use the fact that at 3 p.m. there are 350?
That's time, right? 3 p.m.
So it says at 3 p.m. we have P equals 350. They're telling you the current size at that time, right? Now 3 p.m. is referring to what time? T equals 4, right? They told me about 11 a.m. and 3 p.m. they're measuring time in hours, right? So I'm going to measure time in hours. I'm going to consider that to be T equals 4. This is going to be my P value. This is P of 4. And I know that P naught is 60. So since I know that P is equal to P naught e to the RT, let's start plugging in the numbers. At this point, I know P is 350. P naught, I know, is 60. E is E. R actually don't know. And I know T is 4. So see here, the only unknown is R, and R is one of the things I need to find. How do I solve for R? Right, divide by 60. Then you want to get to that power, so you take the ln of both sides. So I take ln of 35 over 6 equals ln of this. I take ln of this, ln of that. Ln cancels the e. I get 4r. And then what do I get?
4 equals.
R is equal to? Now be careful. The 4 cannot divide inside the ln, right? This is a fortress. You can't go inside the ln. Okay? You can't take something from the outside and multiply inside an ln. It doesn't work. Okay? So that's what your R, that's how you do it. Okay. So now, this means, finally we can actually answer part A. It says find P of T. So in part A, now I know what my P of T is. P of T is equal to 60, which is what I started with, e to this guy, ln 35 over 6 over 4 times t. And that's going to be the answer for A. So that's the function that's going to measure the size of this bacteria population at time t in hours. Part B, what do we need to find for part B? What is the size of the population at 4 p.m.? So basically we want P when T equals 5. Right? Remember, we start the clock at 11 a.m. So 4 p.m. is actually 5 hours away from that. So what do I do now? Just plug in T equals 5. This is 60 E to the ln of 35 over 6 over 4 times 5. I did it. Z. When will the population reach 2,000? Right. Now it's asking the question when. That means it's looking for time. Right? And I want to know when will what happen? In terms of one of these variables that I have. When where P equals 2000. So basically what I'm going to do is I'm going to go to this equation. I know what I want P to be. I need to find the T. So that's it. I'm just going to plug in. Once you have that equation, you can pretty much answer anything. So I'm going to plug in 2000 here. Equals 60. E to the ln of 35 over 6 over 4t. How do I solve for t? Divide by 60. I'm going to ln both sides. ln 35 over 6 t over 4. How do I solve for t? So I have ln of 200 over 6 divided by ln of 35 over 6 and multiply by 4. I can divide these two, right? No. Couldn't catch you. That's basically it. All the problems are going to kind of be like that. It's just a matter of using the information to figure out what your P naught is and what your R is, and once you have those two, you have everything, basically. It's going to be a matter of plugging in something in the function and solving for the other guy, and because you know about E's and ln's, it will be easy to do.
Jhevon, how did the 4 end up in the numerator?
Oh, because it's divided by 4 over here, so I've multiplied both sides by 4. So I have 4 times that ln, and then I divide by the other ln on the right side. You can take 2 steps to do that if you want. Okay, so we're still in string 09. Now it's problem 8. I think on this time, problem 4 was in the compulsory section, and problem 8 was in the optional section. So let's actually see what's going on. So a dosage of 3 milligrams of radioactive iodine is administered for some forms of thyroid cancer. The half-life of this guy is 8 days. Meaning after 8 days, you will have half of what you started with. If the maximum permissible level is 5 milligrams, what is the minimum number of days before a second dosage can be given? So if you're a doctor and you shoot your patient up with iodine, how long can you wait before you don't kill him? Like just giving him more iodine, basically. Assume it's totally absorbed by the thyroid and not excreted by the body. Okay, idea.
So, initial amount is 3 milligrams, right?
So let P be the amount of iodine currently in the body, so let's set up our variables. Okay, so what do we know so far? Right, we know the half-life is 8 days. What does that tell us? In terms of our variables. Coming in?
Is it ln2 over r?
The half-life is the same as ln2 over r. So in other words, what they're telling me is ln2 over r is equal to 8. Now how does that help me?
Because isn't that T?
This is th, the half-life, which as the formula is ln2 over r. So now I can find r. R is one of the things I will need. From this I can tell you that r is going to be ln2 over 8. So I found my r value, which is nice. Also my p naught value would be what?
3 milligrams?
3. That's what I injected with in the beginning, right?
Yeah.
So we're starting out with 3 milligrams of iodine. And that is the growth rate. That's the percentage by which it's decreasing every day. Okay, so we want max I to be, what's the maximum amount of iodine I can
5.
give this person? 5 milligrams.
Milligram.
Which means, how long do I have to wait before I can give them another shot of 3 milligrams?
So,
To give another shot of 3 milligrams, we must wait how long?
LM2/8.
Until,
That's not fine. No, it is fine.
give me a condition for how long we can wait until I can inject them again.
No, he was just to have 16 days? No.
Why 16 days? Are you guys just randomly guessing?
No, but 8 days is the half decay, like half life. So 16 days would be totally.
Yeah, but why are you thinking of everything in terms of halves? We don't have to think in terms of halves. The important thing is the 5. What's the minimum number of days that if I inject another 3 milligrams, I would have 5? Is what we want to figure out, actually. Like the situation where I inject 3 milligrams and it becomes 5, what would have to be true in that case? That means there has to be 2 in the body. So I have to wait until there are 2 milligrams left before I inject the person again. At least, right? That's the minimum number of time I must wait. But this is not really time. This is telling me in terms of an amount. Now I need to figure out the time. So what am I going to do?
How did you figure out P? It's the 2 milligram. P2.
Because each shot is 3.
Mm-hmm.
Going beyond 5 is dangerous. Meaning, if I give you 3, I have to wait until it's at least 2 before I can give you a shot again. Right? Because if it's more than 2 and I inject you with 3, it's going to go beyond 5. Right? It has to be 2 or less before I give you another shot.
Oh, because you can't exceed 5.
Because I can't exceed 5. That's the maximum.
So
It's
you
actually
subtracted
dangerous.
then?
Yeah, I just subtracted.
Okay.
So now, asking me when is the next time I can inject them with 3 milligrams is the same as asking when is it that I have 2 milligrams left. How do I figure out when I have 2 milligrams left?
So
Right, so I know that P is equal to 3, which is the initial amount. E to that R, ln2/8t. So when P equals 2, what we have is 2 is equal to 3 e to the ln2/8t. So the time I need needs to fit that equation.
2/3.
Jhevon, isn't it negative LM2/8?
Where, yes, because it's decaying. It's minus R.
And then they're down there too.
And,
And
right, yes?
And there too, right? We said ln2/r equals 8. That's a -2 also. Minus ln.
No, because in the formula it's minus R.
Okay, so
Right, so that's my R, and I put minus R in the formula, it's decay. Okay, so now I'm just going to solve that same old story. 2/3 is equal to e to the minus ln2/8t. ln both sides. If I get ln 2/3 is equal to minus ln2/8t. This means your t is minus 8 ln 2/3 That's how long I have to wait before injecting money.
So, in English.
And by the way, you always have to worry about whether your answer makes sense. So this negative sign might be alarming to you. Is it fine?
Wait, we have
Alright,
negative
it's
sign?
fine.
Well, because it's decaying. So it's decreasing.
Why didn't we just divide by element of 2 over?
I did. That's what I did. That's how I got this. Dividing by a fraction is the same as multiplying by the reciprocal. Yeah, so how do I know this answer makes sense? Isn't that negative time?
It's negative time because it's half what? So.
No, negative time doesn't make sense to us. We're not in quantum physics. If I told you that was actually a positive number, you think I'm crazy?
You just did it. You just said you could cancel out and distribute it. Like I went to.
This works because ln of 2/3 is actually a negative number. So you have a negative times a negative, which gives you positive. How do I know ln of 2/3 is a negative number? Well, probably the quickest way is to just, yeah, we know the graph of ln, right? It passes through 1 here. 2/3 is less than 1. My y value is going to be a negative number. ln of 2/3 is actually a negative number. If I have a log of anything less than 1, it's a negative number because logs pass through 1 and they get negative after that. Right? So this is actually a negative number, so when I multiply by a negative, it makes it positive, and so this answer actually makes sense. It will take that many days, and you can plug that into your calculator, but you leave the answer like that on the test. That's the answer.
Wouldn't you do like
Yeah, same as ln2 minus ln3, which you, again you would know it's negative, right? Because ln of 3 is bigger than ln of 2. So ln of 2 minus ln of 3 is actually a negative number times this makes it a positive. Tons of this. Okay, let's look at this one. Okay, fall 2009, problem 4 is pretty similar to the other one. So let's actually jump to problem 11. So it says a bank pays 5% interest compounded continuously. Right, so by the way, whenever you see this phrase, compounded continuously, we see this in 209 and other contexts as well. It means exponential growth applies. In fact, the exponential growth formulas come from the fact that we took the compound interest formula and then we assumed that the number of times where compounded goes to infinity. And then when you take the limit, you can use the log rule to take the limit and you'll actually get E as the answer. And so it means that exponential growth is what's applying, meaning all the formulas I gave you for exponential growth is now applying. Right? So that's what compounded continuously means. If you're compounded a specific number of times, you have to use the compound interest formula. Okay. So you have a bank account that pays 5% interest, it's compounded continuously. Suppose you make an initial deposit of $4,000 in the account. A, write a differential equation with initial conditions whose solution gives the amount. Okay, so in part A, it's asking for the differential equation. What does that look like? Right, it says P prime equals RP. In which case, Do I know what the R is? 0.05, because it's growing by 5%. So that's called the differential equation. What it calls the initial condition, it's talking about an equation that describes the initial velocity. So the initial condition is going to be an equation that looks like this. P is a variable. The money is not staying stagnant, it's continuously growing. The only thing that's constant here is the R. I know it's growing at 5%, but it's moving, so I can't plug in a specific value for P. P is a function. The money is continuously growing. So if they didn't tell me about a specific point that I care about, I just write that general form.
I'm sorry, what was R again?
R is the growth rate
Growth.
as a percentage decimal.
Okay.
The initial condition is one that looks like this. It says P of 0 means P at time 0, or P naught. Right? So here you tell them what is it in the beginning. How much do you have in the beginning?
4,000.
4,000. So writing down this equation, you say you've written down the initial condition. That's what this is. It's an equation that describes what you have initially. So that's a differential equation. That's an initial condition. And I'm pretty sure I put that on the first page as well. Yes, I mentioned that the initial condition on the handout. So that's the differential equation that describes the balance of the account. And that's the initial condition that tells me how much it's starting off with. And that does part A. And part B.
You need to know the time to double, right? It takes the double or no?
So it says, at what rate is the account increasing when the principal reaches 6,000?
So what's R?
No, R is the growth constant. It's different from the rate.
What
Here, you
time?
have to remember that rate means derivative. Rate means P prime. Right? Rate and the growth constant are two different things.
So P prime equals R times P?
Right, so I know that P prime is equal to R times P, but they asked me at a specific stage, right?
Yeah.
At what rate is it increasing when it reaches 6,000? So basically this means that the rate when P is 6,000 is going to be, the R is going to be 0.05. So it's going to be that number.
Oh, okay. But we just leave it like that?
Yeah. Let me emphasize that. I wrote it on the handout, but let me emphasize it. The growth constant is not the same as growth rate. It might sound confusing, I know, but rate is always referring to a derivative. Growth constant is referring to the R value. So you have to be careful sometimes when you're reading these things. How long will it take until the principal reaches 5,000? P is
Same
5,000.
thing. It's just 5,000.
So does it see when will P equals 5,000? Now I know that P is equal to 4,000 e to the 0.05 t. This means I need 5,000 equals 4,000 e to the 0.05 t. This means divide both sides by 4,000. both sides to get rid of that e. And so I have ln of 5 over 4 is equal to 0.05t. So my t is equal to ln of 5 over 4 divided by 0.05. That's it. So you'll see a lot of these problems are this kind of the same old story. It's just a matter of using the same problems over and over. You're just reading the ones that reading the information. Let's see if I can find one that's a little bit different. Yeah, in 205 they don't go crazy. It's all kind of the same thing. Let me add a problem to this, something that I might ask in a test. With part D, I can ask something like this. How long will it take to double your money?
So we have to find PD.
Exactly. Which is? ln 2 over
2
r.
over r. 2 over 0. And
I'm sorry, it's really hard to make this a difficult problem.
no, it's not. Not easy.
I mean, if you practice a little bit, it'll be really easy. They're like giveaways on an exam, I think. Yeah, I'm getting bored. Let's jump to related rates.
Can we do a review
A review of what?
of some problems in the exam?
Let me think about this.
Let's take your time.
Not too long though.
I can do a short review on Tuesday. How about that? Yeah.
Why don't we just review the whole entire class?
No.
We can do this and then
We can
today.
review the last 40 minutes.
Yeah, on Tuesday.
But it's short today too.
Why not today?
Because I want to make sure that you all go home this weekend, you do the homework, you do the review,
But you
you
don't
actually
have to do
attempted
that.
everything.
Yeah, but it's better.
Remember, the watching you do something is very different from trying it on your own. I need to make sure everyone tried everything on their own. Did everyone do everything in the review already?
Yes.
No, not everyone. Did everyone do everything in the review already? No. This weekend, do everything in the review, and then on Tuesday, if you have questions still, then review.
Sounds fair, okay.
Okay? All right. Let's go to related rates. These are a lot more fun.
Yeah, that's when we heard from like that.
Because things vary with related rates, so that's why it's fun. So it's not always the same exact formula. The good news, though, is it's always the same process. You always go through these steps in this order. So it's a really nice method, and I like it. Optimization is also very similar. It has a lot of variation, but it's kind of the same process. So this is one of the situations in which algorithms comes in handy, not just formulas. So there's not a specific form per se that applies to this, but there is a specific algorithm. So you just have to figure out when you're faced with a related rates problem, and you know that this is the algorithm that you're going to go through all the time. Okay. So let's talk about that. So there's a little intro blurb here. Related rates just talk about the rates of change of two different quantities. It could be more, but in 205 we'll usually be doing two. That they actually relate to each other, or the rates of one affects the other one, right? And we might know the rate of one, and we want to figure out how fast the other one is moving at the same time, right? So that's called related rates, essentially. Okay? So you're measuring the rates of change of two quantities that depend on each other, and so now you know that their rates depend on each other when the quantities depend on each other. And you're going to use this process to figure out how to solve for any unknowns that you need. So here is the method. Step one, read the problem carefully. This is very important that you read the problem carefully, right? Because how you're going to set things up is going to depend very, very much on how the problem is phrased and what you're even looking for in the first place. So it's very important that you read the problem carefully. We'll look at that. We'll look at some, because the problems for related rates, they're always like word problems. So you're going to have to read carefully so you know what you're looking for, what you want to set up, etc. Right? 2, if it's possible, draw a picture. Right? Label the quantities that are changing with variables, label the quantities that do not change with constants. Which means you need to read the problem so you know who is a constant from who is a variable, who is changing from who is not. Right? Because that will help you in part 2. Part 2, you can draw a picture. You might not always need to draw a picture, but if it's possible, do it. Okay. 3, you're going to write down the given information. Right? You're going to write down what you know, and you're going to write down what you want to find. Right? So I put that step in there. It's not necessarily helping you solve the problem, but it's good to give you a target. Right? Because sometimes these problems, you get lost in the algebra. I see students do it all the time. They're doing it and they're like, what am I looking for again? So step 3, write down what you know and what you're looking for, and you do not stop until you get what you're looking for. Okay, so you write it down, and I'm going to show you how to do that as well. Okay, now here the fun part starts. 4, you're going to set up an equation that relates the quantities that you figured out in step 2, right? A lot of times it will focus on the picture. So for example, if your picture is a rectangle and the problem is talking about area, you can know that it's just length times width. It helps you to set up that formula from the picture, right? And right, so 4, that's gonna be what you set up, right? If you drew it, and I say here, if you drew a diagram, it will usually come in handy. So if you know it's a triangle, you can think Pythagoras' theorem. You can think, well, we don't do trig. I mentioned sines and cosines here. Or if it's a rectangle, you can think of length times width. You can think of perimeter. You can think of anything that would apply to that diagram that you drew. And you can use that to set up an equation. 5 is where the calculus comes in. You're going to differentiate the equation implicitly with respect to t. Because we're talking about rates, it means time is the independent variable. Then in part 6, you're going to plug in what you know, solve for what you don't know. Pretty simple there. And the thing is, sometimes you won't have all your knowns right out there, out in the open. Sometimes you have several things that you don't know, but you can always go back to that formula that you set up in part 4 and figure out anything that you need to know that you don't already know. Right? So, I wrote this very suggestive. When you're working on these problems and you're practicing this, right? Read through the algorithm every time so you can sort of see what it's about, etc. And the kind of ideas and what you should be thinking about when you're doing each step. That's what these words are. What I put in bold, right? See here I put some words in bold and some not in bold. That's because when you're studying and you're actually doing your study sheet, by the time you get to the point where you're actually ready to sit down and study for a test and you're making a study sheet, you would only write the things that are in bold on that study sheet. Right? Because by that time, you're so used to reading everything, once you read that sentence in bold, your mind will already remember all the things that is not in bold. It will trigger a memory. Right? Why you want to only be concise is because of how your brain works. Your brain works very well with small snippets of information. Right? So you don't want to have this whole thing memorized in your head. Read it over so that you get comfortable with it, memorize the things in bold, and it will be just as good as you memorizing everything. Okay. Now, let's actually jump into an example. So this is chapter 1. Related rates. Oh, by the way, let's let's just mention here. You know you have to do this method. Because now we're going to talk about a lot of applications of derivatives. There are going to be several things that are word problems, and you're going to need to know, when does a word problem mean I have to do related rates, or optimization, or exponential growth and decay? When do I do what? Right? So you know you're faced with a related rates problem when the problem refers to the rate of change for the quantities, or how fast they're moving, etc. So there's going to be a word problem that's going to say, okay, there are these two things here. This thing is moving this fast. How fast is this thing moving? Right? Whenever you see that kind of word problem, it's a related rates word problem. So you're going to look for the word rates. The word rate it's pretty much always going to show up in a related rates problem. You may see how fast or how slow something is moving, but it's always related quantities. So it's not going to just be one thing that you're focusing on. The problem will always have two or more things that are connected. And then it's going to talk about how fast one is changing. Whenever you see that, it's a related rates problem. It means you need to go through these 6 steps to solve the problem. Okay. Here's problem 1. A right circular cylinder. By the way, you're going to have to remember all your formulas from geometry. It's going to be important. So review that if you don't know. Stuff that have to do with triangles, rectangles, circles, cylinders, boxes. You're going to need to remember them. Surface area. No. Okay, so let's read. A right circular cylinder undergoes expansion. The radius is increasing at a rate of 1 meter per second, while its height is increasing at a rate of 2 meters per second. At what rate is its volume changing when the radius is 1 meter in length and the height is 3 meters in length? So you're reading this problem. Notice that there are several quantities mentioned. They talk to me about the radius of something, the height of something, and its volume. Then they tell me how fast a couple of the things are changing. They tell me the radius is increasing at this rate. The height is increasing at that rate, right? That tells me it's a related rates problem. I have several quantities that are related, and they're telling me how fast some of them are changing. So I know it's a related rates problem just by reading that. Okay, so step 1, read the problem. So I read the problem carefully. Now I know what is changing and what is staying constant. Step 2, you can draw a picture. Right circular cylinder means that's the picture. The radius is going to be the distance from the center to the outer edge. The height is just going to be how tall it is. Okay. So here, notice that I labeled the radius R and I labeled the height H. Okay? Why? Because they're both changing. If the problem had said something like, the radius is changing at this much, but the height is 5, I would write 5 here, right? I would not write H, right? Anything that's changing, I need to label it with a variable. Very important. Okay. Right? So I know the height is a variable and the radius is a variable. How do I know? Because they told me that the radius is increasing and the height is increasing, which means they're moving, they're not constant. Right? So I need to label both with a variable. So you draw that right circular cylinder, and then what may happen, you might start to have flashbacks about high school geometry. You start looking there's no place like home. After you get through that phase though, that's going to trigger, oh yeah, I remember that formula that has to do with cylinders, right? So now in that picture there are two things represented. There's the radius and there's the height. Notice that in the question though, They mentioned another quantity, right? What did they mention here? They also mentioned volume, right? Anyway, let's go to step 3. It means volume I'm going to have to put in there somehow. What was step 3?
Write down information.
Write down what I know. Write down what I want to find. Right? This is giving me a target. Okay. What do I know? Sure, I know the rate at which the radius is increasing, which is dr dt, or r prime, where the independent variable is
with
t.
respect to t.
And it's increasing at 1, right? Well, its height is increasing at a rate of 2, so I also know dh dt is 2.
Can we just write h over dt also?
No, it has to be dh dt. You could write h prime, but I'd rather you emphasize that there's a function of t. It'll be this. You could write that. But I'm usually going to write it this way because I'm spoiled by Calc 3 where there are tons of variables all over. Alright, so this is what I know. I know how fast the radius is changing. I know how fast the height is changing. And what was I asked to find? I want to find the rate of change of the volume, right? So what do I want? I want dV dt. When do we want it? Now. No. When do I want dV dt?
When the radius is 1 and the
Radius is 1 and height is 3.
Wait, how do you? Oh, okay. Yeah.
Right? So it says, at what rate is the volume changing when the radius is 1 and the height is 3? So these are the things I know. This is what I want. This is the condition under which I want it. Write that down. So you know, if you don't know what dV dt is at the end of the day, when the r value is 1 and the h value is 3, you are not done. Okay, so we know where we're headed. 4. Now I'm going to have to come up with a formula that relates all the variables in the previous steps. Now the variables I have so far is r, h, and v. Do we know a formula that relates r, h, and v for a circular cylinder? Right, the volume of a cylinder is pi r squared h. Right, the volume of any uniform prism is the area of the base times the height. The area of a circle is pi r squared, and the height is h. So that's going to be the formula that I'm going to come up with. This is a formula that has the v, the r, and the h. It has every single variable that I mentioned before. That's important. It has everything. So that is step 4. Now, what?
One question. Is it also because it says at what rate is its volume changing? Is that why we need that formula of volume?
Yeah, because it means I want this, right? But in order to find that, I need to find the v,
Okay.
right? Because it's asked me to find the derivative of v. I need to know what v is to find the derivative. Right? So I know I need to find the v, I need to find the r, I need to find the h. I need a formula that relates all of these, and that is a formula. Okay, so that is step 4. Now step 5. We're going to differentiate implicitly with respect to t. Now that word implicitly here is basically telling you that your v, your r, your h, they're not variables by themselves. They all are functions of t, right? That's important. So that means whenever I differentiate a v term, I have to multiply by dv dt. If I differentiate an r term, I have to multiply by dr dt. If I differentiate an h term, I have to multiply by dh dt because the chain rule takes effect. Okay. So when I differentiate this with respect to t, what am I going to get? Right, the v with respect to t is just dv dt equals
times h plus pi r squared dh dt.
You guys see what she did? It's product rule. R is a function, and h is a function. There are two things multiplying. You can't forget the product rule. That's why every beginning of every class I always ask you to remind you, remember the formulas, guys. See two things multiplying, you need the product rule, right? So she differentiated the r squared, gives me 2r dr dt because of the chain rule. Then you have to plus, you just leave the r squared alone, differentiate h, gives me dh dt. So this is the equation I get when I differentiate implicitly with respect to t. Now I know, what is it that I actually want? dv dt. When do I want it? When the r is 1, when the h is 3. So it means I can plug in 1 here, plug in 3 there, plug in 1 there. What else do I know? I know what dr dt is, and I know dh dt. So I actually know this, and I know that. I know everything. Pi is a constant, it's just pi. So this means when r is 1, h is 3, what we have is dv dt is equal to 2 pi times 1 times dr dt, which is 1, times h, which is 3, plus pi times 1 squared times dh dt times 2. So that's basically 6 pi plus 2 pi, which means this is 8 pi. It's growing at 8 pi, it's meters per second. So it's meters cubed per second. I don't care about the units, but I'm just writing. 8 pi. What? Volume is cubic units. Right, so that's no, I don't care. We're about units when you're in physics. I don't care. Right? So 8 pi would be the answer. Right? So if my radius is changing by 1, meaning after every second, my radius gets longer by 1 meter, and my height gets longer by 2 meters, my volume will get larger by 8 pi cubic meters. It will be growing that fast at this point. Any questions?
Because it's 2 pi. So it's 6 pi plus 2 pi.
Yes, you need the product rule, right? All your goal derivative rules still apply. Product rule, quotient rule, chain rule, all that.
Would that be step 6?
That's one example. Let's do another example. So that one was kind of straightforward, relatively speaking, believe it or not. Because that's one where I ended up with this and I knew everything that I needed to know right there. I didn't have to backtrack, I didn't have to figure anything out. It's not always going to be that easy. So let's go to example 3. I might come back to example 2, but I like this one. So example 3 from the handout. Okay, so step 1, read. Okay, let's read together. Okay. A 15-foot ladder was resting against a vertical wall. Suddenly and without warning, the foot of the ladder begins to slide away from the wall at a rate of 2 feet per second. At what rate is the top of the ladder sliding down the wall when the foot of the ladder is 9 feet from the wall? So again, here, if I saw that on a test, I realized, hey, they're telling me about several things here, about how far the foot of the ladder is away from the wall versus the height, and they're telling me how fast the rate of something is changing, and then they ask me about another. It's a related rates problem, right? So 2. The diagram is going to be, it's essentially going to be a triangle, right? So if this, I draw that, that's the wall. This is the ground. And this is the ladder resting against it. Right? So basically, my diagram is going to be a triangle like this. Now, how am I going to label this triangle? Huh?
This is the height.
So what do you want me to label? Huh? Y. Right? This one? X. This one? That's why we agree. The ladder is 15 feet. The ladder is not growing, right? So this is the ladder resting against the wall. It's a 15-foot ladder. I'm not going to label it with a Z because Z means a variable. It's 15. It's always going to be 15. Okay? So that is my picture. There's an X, there's a Y, because these are changing. What's happening is the foot of the ladder is being pulled away from the wall, so my X is actually getting bigger. At the same time, the Y, it's sliding down, so the Y is getting smaller. So this length is changing, that length is also changing. But the ladder is always going to be 15 feet long. So that's a constant, right? These two are the variables. Okay. Right, so now step 3. What do I know? What do I want? So let's talk about the rates in terms of, yeah, I know ladder is 15, that's
We
here.
know dx dt is 2.
Dx dt is 2, right? When this is moving away, it's increasing by 2. We'll talk about positives and negative signs in future examples, but that's a 2. Okay. What else do I know? That's all they told me right here. What do I want?
dy dt.
I want to know how fast is it sliding down the wall. That's how fast the y is changing. When do I want it? Now. When what is? When x equals 9. Okay? So this is what I know. Here's what I want. Here's the conditions under when I want it.
How is it that dx over dt is 2?
Huh?
How is it dx dt is 2?
It says the foot of the ladder. This is the foot of the ladder. It's sliding away. It's sliding away in that direction. Away from the wall. Which means my x is getting bigger. And it's getting bigger by 2 feet per second.
What if y and x were switched? Wouldn't it be a problem?
No, then you'd have dy dt equals 2 and dx dt here.
Okay.
Just make sure once you draw your diagram, your equations use the variables in the diagram. So it doesn't matter what you call what. It won't matter. Okay, so that's my picture. That's what I know, and that's what I want. Alright, so now we have a target. Next step is to do what? I need to come up with a formula that relates all my variables. The only variables I have here is x and y. Do I know a formula that will relate the x and y? Right, it's a right triangle, so there are two things I'm going to think about. SOHCAHTOA and Pythagoras' theorem. SOHCAHTOA is never going to apply in this class because we don't do trig. So that makes it a lot easier. Pythagoras' theorem is what we're going to do. Right? SOHCAHTOA would help us with angles, but Pythagoras' theorem helps us when all we care about is side lengths. So for this particular right triangle, what would Pythagoras' theorem say? Equals 15 squared. Okay, so that's my equation. Now step 5, what am I going to do? Differentiate implicitly with respect to t. My x is a function of t, my y is a function of t, so I'm doing implicit differentiation with respect to t. What do I get? Zero of 15 squared is 0. So now, what do I actually want? Let's not forget that. I want the dy dt. I want this guy. So let's actually solve for that guy.
Wouldn't it be dy dt first?
Wouldn't it be what?
You could go back there and find
The
your
derivative.
Well, this is what I want. Let's solve for that first. So I solve for dy dt. I would get what? Minus 2x dx dt over 2y 2. So this is minus x dx dt divided by y. Right? Now, I know my x. I know the dx dt. Do I know y?
No.
Yes.
Why didn't you just use that equation?
that is what I would do. That's what we're gonna do. The thing is, at this point, you're gonna want to plug in to start getting your answer. You're gonna realize, hey, I know the x, hey, I know the x dt, but what is y, right? If there's something here that you don't know what the answer is, it means you can figure it out from the equation that you set up before. So here, we need to find y. Yes. This from this to this. Oh, I just solved for dy dt. Subtract
Why
this.
did you write x prime and y prime? It makes it easier for us, no?
Okay, so write x prime. Just write x prime.
Yeah, I was making something. No, I did.
Forcing you, right?
I personally think that's easier.
Okay.
Yeah, it tells me what it is. When I just
We need to find y. How do we find y? Well, go back to the equation. Go back to step 4. So what happens is, I have 9 squared plus y squared equals 15 squared. Okay, who can tell me what y is quickly? What? You're thinking too hard. Does that help?
It is 12.
What?
I'm serious, it's 12.
How did you get that?
The factor is here.
Did you actually find 15 squared?
Yes.
Yeah,
Minus 9 squared.
There's an easier way. That's what I'm trying to say. It's 3, 4, 5. That's what I want you to remember.
It's 12,
Remember
yeah.
from high school geometry, there are triangles that have certain relationships. There's what's called the 3, 4, 5 triangle. I tell you, there are going to be cases where these numbers are going to be big. You don't have a calculator. You don't want to have to do unnecessary calculations. There's something called the 3, 4, 5 triangle.
Yes.
Right? Meaning if you have a right triangle where the hypotenuse is 5, one side is 3, the other side has to be 4. You don't have to waste time calculating. So if you know this is 4 and that's 5, this has to be 3. If you know this is 3 and that's 5, this has to be 4. If you know that's 3 and that's 4, that has to be 5. Right? They always will relate to each other. Whenever the hypotenuse is 5, one side is 3, 4, 4, the other number will fill in by itself. One thing you have to remember is that this also works proportionally. Right? So if I can multiply all sides by the same number and the relationship will hold. Now the thing is here, this was a 9, that's just 3 times 3. This was a 15, which is 5 times 3. Therefore the remaining angle is just going to be 4 times 3. Right? So I'm going to look at 15 and I'm going to notice that, hey, that's 5 times 3, that's 3 times 3, so that must be 4 times 3, it's 12. Right? Which is going to be a lot easier than figuring out what is 15 squared and then figuring out what's 9 squared and then subtracting the 2 and make mistakes with the arithmetic. Right? Right? So in the 209 final in the test, this is a very common relationship because they know that you can't use calculators, so they actually give you, believe it or not, they give you very nice situations, right, where they will all go together.
But these are bad numbers, Jhevon.
What other special triangles do you have? There's also the 5, 12, 13 triangle, right? Which means if that's 13, and you know the other side is 5, then this side must be 12. Or vice versa. Right? So if I gave you a triangle where I said, oh, this is 169, that's 144, solve for this guy. If you want to sit down and compute 169 squared, and then compute 144 squared, and subtract those two, be my guest when you have 15 other problems to do. Or you could just realize that this guy is just a third.
No, it's
It would be, this would be 12 times, what's 12 times 13?
Yeah, that's 144.
Yeah,
156.
No, it's not 144.
12 times 12 is 144.
144, and then
12 times 12.
it's 144.
No, 12 times 13, what's 12 times 13?
156.
144. No, that's 12 times
12 times 12 is 144.
156.
Okay, So if I give you a triangle where this is 169, that's 156, you know that this side would have to be what?
I don't know.
Because you know this is 13 times 13, that's actually 12 times 13. So this side would be, it'd have to be 5 times 13. Right, so it saves you from getting the squares. You can just get it short. Okay, so we know from here the y is actually going to be 5. It's going to be 12, according to the 3, 4, 5. So here, if we know that 9 squared plus y squared equals 15 squared, then y equals 12. And you're welcome to do the arithmetic if you want, but if you get it wrong, don't expect me to like be lenient. Okay, so y is 12, and now I can go back to that line. So I know my dy dt is minus x dx dt, or y prime is equal to minus x times x prime over y. And now at this point, now I know everybody. My x is 9. My dx dt is, I don't know, we wrote it down, sorry. 2. And my y I just figured out was 12. Right? So I read to this, it was 3 times, and that was 4 times, and then it was 2 times. So I have negative 3 over 2. Now, what does that negative mean?
Decreasing.
Why is
Because it's a third amount. The
Well,
rate
it's not negative because it's like increasing.
Decreasing. That's what we're going to look at. Remember, positive slope means increasing, negative slope means decreasing. So the answer, what we can say, they asked us, what did they ask us?
At what rate?
At what rate is the top of that slide down? So you can say, well, that would be your answer. dy dt is equal to minus 3 over 2 at this instant. And how you want to interpret that is you might have to do it for some other terms. What this means is that y is decreasing. By 3 over 2 feet per second. Right? That's what this negative sign means. You can interpret it as decreasing, which might come in handy otherwise. So if a rate is positive, it means it's increasing, meaning on your diagram that thing is getting bigger. And if it's negative, it means on your diagram that thing is getting smaller. Let's keep going. By the way, some like, yeah, 1, 2, 3, 4. Problems like that are actually pretty common for a test. Your homework would have a lot of problems like the baseball problem. But let's keep going. Problem 7 is also kind of really quick. Except they might say something like an airplane. Let's do problem 4 from handout.
This is last one.
Step 1, read the problem. Okay, so let's see what's going on. A new ship A is 80 miles west of ship B. At this time, both ships set sail. Say at 2 times fast. Ship A sails south at a speed of 20 miles per hour, while ship B sails north at a speed of 10 miles per hour. How fast is the distance between the two ships changing at 2 p.m. if they both maintain constant speed? So, let's actually go to step 2. What is our picture going to look like? So here's these guys here.
Yeah, that helps.
So it says it starts out where ship A is 80 miles west of ship B. So it means A starts here, B starts here, and this length is 80. Now at noon, what starts to happen? Ship A starts sailing south. B starts going north. And how fast is the distance between them? So currently these guys here, that's the ship A, that's ship B. What's the distance between them? That diagonal, just connect those with a line. So the distance between them would be represented by that line. Okay. So let's actually start putting some variables in. Right? What is the things that are changing? Well, this distance is changing because it's keep moving, right? So let's label that something. Let's call that x. This distance is also changing because that's increasing. Call that y. This distance is the one that they asked us about, which we care about. Notice that as these move apart, this is also changing. It's increasing.
Yeah.
So call this length like a z or something. Okay. It's z.
Which one?
So there's a picture. So 3, what do we do? Right now, what we know, what do we want?
How long does this usually take on an exam to do?
What's hard? Well, this will be a problem by itself, usually. So a related rates problem usually won't have like parts to it. It'll just be like, boom, this question is a related rate.
We know the distance between A and B initially.
What do we know?
We know that Z is equals to 80.
No, not C.
Something similar. Next week? No, we finished the test though. The last thing that's on the test next week is marginal analysis. What? This could be a bonus. This is the topic right after the test topics. So if I'm giving you a bonus, it would be on this and exponential growth. Okay, so what do we know? I know dx dt, I know how fast ship A is moving. What is that?
20 miles.
20. So the length x is increasing by a rate of 20 miles per hour.
dy dt 10.
And dy dt, 10. And what do I want? I want the rate at which the distance is changing between them. When do I want it? How do I describe that in terms of the variables I have?
T equals 2. Time.
What would x be? What would y be? Sure, they're constant speed.
It's the same thing we did before with the time.
We start when? At noon, and we're measuring things at 2 p.m., right? So how far will A get at 2 p.m.?
40 miles.
40.
40 miles.
40. Right? It's moving 20 miles per hour, and it's traveled for 2 hours. So we would have covered 40 miles in 2 hours.
So it's
What about Y?
20.
Y would be 20. So I want this under these conditions for max and Y. Okay. 4. An equation that relates everybody.
Okay. Let's see.
Don't shout out at once. Give me an equation that relates X, Y, and Z.
Would you do 2 times Pythagorean theorem? Like,
Well,
it's the,
I don't really know how that hypotenuse relates to that hypotenuse, though. Huh? Sure. So what does that mean? So let me show you.
would it just be a
this.
rectangle?
Another rectangle.
Ah, too complicated. Just do part of it. Notice that if I do this and that, what do you see?
A rectangle.
You see a rectangle.
Or a big triangle.
A
You see a
triangle,
big
yeah.
triangle here.
But don't you see a rectangle?
I see the rectangle.
No.
You don't see the rectangle though?
Is that one? Do you see that skull of the woman looking in the mirror? Okay, what do I actually see? Well, there's a big right here.
Ooh, is it reflective?
What would this length be here?
Y plus the X.
X plus y. What would this length here be? That's 80. And this is
Z plus X.
80. Right? So from this,
Oh, the Z, yeah.
that's actually a picture I would use.
Wait, the whole thing is gonna be C?
Yes. Z is the distance between the two ships. Right? Very common term. So what is the equation here? No, that's an old thing. That's
So that's what we're working.
yeah, I'm working with this. Because that one was just too confusing. You couldn't even figure out a form for that. That is equivalent. It uses the same variables. Gives me a different picture. Can I figure out an equation from that?
Yeah.
Wait, is it gonna be 4, 5, 3, that triangle? Because 80.
I don't know yet. But let's what is the equation that relates them?
The X plus
Pythagoras theorem again. So that's going to be what?
X squared plus
X plus y squared plus 80 squared equals z squared 5. How do I differentiate that with respect to t?
wait, is next
The x dt plus dy dt. What? I'm doing the chain rule. Differentiate the outside, multiply, derivative the inside. Derivative of 80 squared is 0, derivative of z squared is 2z dz dt, or z prime.
Z.
Twos would cancel. Now, I know these two. I actually know these two. Who do I not know?
Z.
Z. I don't know where Z is coming from. There's no Z in this problem. There's a Z.
That's a
You've
C.
always
I see right here.
Jhevon, they call us like Z.
Okay, so what does this mean? So what I have here,
You go back to the original equation.
go back to that equation,
And you
right?
plug into.
Now I know my x is 40, my y is 20. So what I have here is 60 squared plus 80 squared equals z squared.
Z.
And what is that?
Z would be 100.
How'd you get 100?
Because 3, 4, 5, so it'd be 6 and 8, so that's by 2. So
How do you see it's 3, 4, 5?
because I just take out the zero.
I said 3, 4, 5 from the beginning.
Right, 60 is actually 3 times 20.
20, yeah.
This is actually 4 times 20. So that side must be 5 times 20. Right? And z
That's
equals 5.
what I thought. 4 times 20.
And now I remember. This means, start to plug them in. X plus y, so this means I have 40 plus 20 times dx,
20.
which is 20, plus
10.
dy, which is 10, equals z, which is 100, times dz dt, which I don't know, that's actually what I want to solve for. I canceled 2's from both sides. There was a 2 here, there was a 2 here. I divided 2 by both on both sides. Which means dz dt is just 40 plus 20 times 20 plus 10 over 100. 4 plus 20 is 60 times 30 over 100. That cancels, so it's 18. 18 miles per hour is how fast the distance between them is changing. So the distance between them is changing, increasing at 18 miles per hour. we'll stop there. We'll do more examples on Tuesdays. You can actually try these at home before Tuesday. So you can get through quickly and then we can do some review at this.
You have a quiz on Tuesday?
7%. Yes. So at least you'll be tested on everything you need for the test. You have been tested on it on a quiz, so you kind of know where you need to.
Is the quiz going to be on what we just learned?
Huh?
Is the quiz going to be on what we just learned?
It's on everything since the last class. Well, you won't be able to get Tuesday's quiz before, but I'll post the solutions so you can go home and try again.